Math 31. This is a lesson on operations with functions, and it's covering a fairly obscure topic in functions. It doesn't get used often nowadays, but you will find a few of the topics will be somewhat useful. And for your information, it all starts with this. If you took an ordered pair x, y, any ordered pair x, y, another word for the x-coordinate is the abscissa. And then the y is the ordinate. And these get used when we're describing operations with functions. So the addition of ordinates, which is the first one, is really the addition of y-coordinates. And that's what that means, and it becomes significant when we really analyze these later on. So if you were given functions, say x and y, just any sort of thing like this, this statement is true. If we are adding two functions together like this, we can write it like this, f plus g at x. And it really just simplifies down to f at x plus g at x. Now don't turn this into something complicated. For example, if you had f at x is equal to x squared, and g at x is equal to x plus 1, this really would just mean that if we were to add these together, f plus g at x, we would be just adding the x squared plus x plus 1. So nothing really remarkable about it. And this would be true even if you did have non-polynomial type functions. Now something that does matter is the nature of the domain. The domain of this new function, f plus g, is going to be equal to the domain of f and domain of g. And that symbol in between, that upside down u, means intersection of. An intersection of simply means the and. It means the word and. And it means that we're looking for the x values that are common to both f and g. So they have to be common to both, and that's the way these things work. They have to be, the word and implies that it satisfies both. So that will have an effect later on. Now if we looked at a simple example, given the functions f and g below, here they are, we want to find f plus g. So the first thing that we have to do is get the domain of f plus g. And as was noted earlier, the domain is going to be the common or the shared x values, the intersection. They have to be in both f and g. So we take a look and we see that we have x is 2 in this one. We do a scan through the g function and we see that it also has x equal 2. But then when we do 3, there's no x equal 3 in g. There's no x equal 4 in g. There's no x equal negative 3 in g. So we're shut out until we get to 0, because that is common to both. And it means that our domain for f plus g is going to be just those two numbers, 0 and 2. That's not an ordered pair, that's me just listing them. And now, when we want to get the actual function itself, f plus g at x, we only work with those two x values, and we also work on the principle of addition of ordinates. Now that means that when x is 0, to get the y value in the new function, f plus g, we have to take the first negative 1, the y-coordinate for x's, when x is 0 in that function, and then the y-coordinate there. So it becomes negative 1 plus 1. So we add them together. And then for x is 2, we note that y is 3 for the f function, and we add it to y is 7 on the other one. So we do whatever the function tells us, or the operation tells us to do, which in this case is add. And it would therefore mean that the ordered pair is 0, 0, and 2, 10. So that's how that works. Now the other thing that you run into quite often is not just a set of ordered pairs like this, but we're actually given functions such as this. F at x is x squared, g at x is equal to negative x. Now we just want the domain, but I know you're probably thinking we should probably write the function out. So f plus g at x is simply the sum of these two. So x squared plus square root of negative x. However, with respect to the domain, since f at x is equal to x squared, we have to be aware that the domain for this function has no restrictions. It's a quadratic, and also we know that it has no restrictions because there's no reason we couldn't put any x value in for that. So there's our domain. And then we do the same thing for g at x. This is an interesting one because it has a radical square root, which means that we have to look underneath the radical, and the radicand, and be aware that this negative x has got to be greater than or equal to 0. Now don't be put off by the negative and say, well, nothing works for that. Because when you simplify this by dividing by the negative, remember you reverse the inequality and divide by negative 1, and it becomes x is less than 0. So it just means that x must be a negative number so that negative negative makes it positive. However, when we write the domain, it means it'll be negative infinity as a lower limit to 0 inclusive. And then you ask yourself, what are the shared x values between those two sets? And the answer would be from negative infinity to 0. Has to be, right? Because that's they have to be both, satisfy both sets. So the actual domain, which is what we want for this one, of f plus g is going to be equal to negative infinity to 0. That's how that works. Now, the next thing we'll look at is just the other properties, but they work the same way, really. Subtraction of ordinates looks like this. You're just subtracting the two polynomials. Multiplication of ordinates, got to get used to the notation a bit, f times g written like that, but it just means that you're multiplying the y coordinates. So it's always the y coordinates that get multiplied, or whatever operation you have. And division the same. Being aware, of course, that the quotient, or the divisor, the denominator, cannot be equal to 0. So that will put a restriction on the domain. And also be aware that in all cases the domain is going to be the intersection of f intersected with the domain of g. So it's whatever is common to both. And when you're doing this, when you're using it, you typically use it for questions like graphing problems, because it allows you to take graphs, functions that you don't know, and graph them so they're unfamiliar. And if you don't have a graphing calculator in front of you, this expands the number of graphs that you can handle, particularly if they get combinations of sine and cosine or logarithmic graphs. They can get messy. So this will help. So first, if we want to sketch y is equal to 2x times x squared minus 1, you're probably thinking, I could just distribute that 2x in and be done with it. And you could. But I'm going to keep it broken down. I'm going to recognize that if we called this 2x f and this other one g, this really is f times g. And I'm going to do each one separately. So I'll bring up a graph for each one of them. First off, this one. And even though I didn't really show it well on the grid, this does go forever left and right. So the domain is going to be all real numbers. And then let's take a look at the next one. the g function is x squared minus 1. So here's our g at x. It's a quadratic with a vertical translation of 1 unit down. And in this case, the domain is going to be all real numbers, so no restriction. Now, that's going to tell us that the domain of f times g at x is going to be all real numbers. Makes sense, because the intersection of those two infinite sets would still be an infinite set. So that's good. Now let's take a look then at the traditional method of solving these ones. So usually what we do, get the graph out of our face for a while, is we set up a multi-columned table of values. And then the first one to the left is x. Then the next column would be f at x. So here we plot the f coordinates, the y points for that one. And then we do the g ordinates in the next one. And the very last one would be f times g at x. And I know you could graph or plot any x coordinate you wanted, but I'm going to pick nice simple ones. -1, 0, and then 1, and then 2. So just around the axis so I can see what's going on. And so for f at x, here's your f function, here's your g. You simply plug in your x coordinates and get the corresponding f value. So you replace -2 into the f function. It's 2 times -2 is -4. And then you replace x as -1. 2 times -1 is -2. 2 times 0 is 0. 2 times 1 is 2. 2 times 2, 4. And then the g function, we replace x with -2. -2 squared is 4, minus 1 is 3. Then -1 squared minus 1 is 0. And then 0 squared minus 1 is -1. 1 squared minus 1 is 0 again. 2 squared minus 1, 4 minus 1 is 3. So now we multiply these two together. So -4 times 3 is -12. -2 times 0, 0. 0 times -1 is -1. So all I'm doing is multiplying the ordinates, the two y coordinates for f and g. And by the way, 0 times -1 is actually equal to 0. 2 times 0 is 0, so this times this. 4 times 3 is 12. And you're probably getting a little concerned. All those zeros for the y coordinates. So to give us a little more information, I'm going to go back and I'm going to pick a point between 0 and 1/2, because I'd like a little more detail. And if I plug in 1/2 into this, 2 times 1/2 is 1. And then if I plug 1/2 into the g function, be careful, but 1/2 squared is 1/4, minus 1 is -3/4. So you can check that out if you don't believe me. And it would mean our new y coordinate is the product of those two, -3/4. So the points we're concerned with are when x is -2, our new y coordinate is -12. When x is -1, the new y coordinate is 0. When x is 0, the new y coordinate is 0. When x is 1, the new y coordinate is 0. When x is 2, the y coordinate is 12. And then finally, when x is 1/2, -3/4. So let's see what this looks like. And we have to plot these. But here's -2, -12. I'll get that one roughly drawn in down there. And then we had -1, 0. We had 0, 0. We had 1, 0. And then we had 2, 12. And then just to help us out a little bit, when x was 1/2, y was -3/4, which is about right there. And we just connect the dots basically. This would be a little rough. And already I went too high up because that other point would be it'd be perfectly symmetric. So I should have probably got that x equal -1/2 just to make this one perfect. But there we go. It's not beautiful, but it's basically correct. And I also do have it graphed so we can get a better look at it. So here is the f function, y is equal to f at x. Here's y is equal to g at x. And here's y is equal to f times g at x. So that's a better graph, the dark one. And as far as drawing it the way I did, really, I wouldn't get too worked up about it, but it's just connecting the dots. You know that this one, if it has these, I'm going to take it back for a second. If it, the other graph looks much better. If these are your x-intercepts, you're basically just connecting the dots. In order for it to go from this point down there upwards, it has to come up towards the x-axis. It has to turn around, go through the other one, and then come back up again through the next one. So you're just taking the points and you're connecting them. And you find that you don't really have a lot of choice. Anyways, that's it for that lesson. That's pretty much all we can do. There is on your handout, if you did copy the notes down, there's another question, but it's just an addition one. You can graph that one if you'd like and check it on your calculator, but I'll just leave it with as much as I've done. The next lesson will be on transformations of functions. So thank you for